Welcome and thank you for standing by. At this time, all participants are in a listen-only mode until the question and answer session of today's conference. At that time, you may press star 1 on your phone to ask a question. I'd like to inform all parties that today's conference is being recorded. If you have any objections, you may disconnect at this time. I would now like to turn the conference over to Dwayne Brown. Thank you. You may begin.
Thank you, operator. Welcome, everyone, and happy Thursday. This is Dwayne Brown from the Office of Communications, and today you will hear the research being published today in the journal Science that explains why carbon dioxide levels in Earth's atmosphere took a big jump in 2015 and 2016. And critical to these findings were data from NASA's Orbiting Carbon Observatory 2, or OCO2, the mission which was launched in 2014. We've got a lot to cover, so just a few housekeeping notes. Participants will be having graphics and calling for the graphics. So just in case, if you want to see those graphics, they're obviously on www.nasa.gov, specifically nasa.gov/OCO2telecon, all one word, nasa.gov/OCO2telecon. We'll also be taking questions from social media, as always, using the hashtag AskNASA. And, of course, all of the information you hear today and much, much more will be on the website at www.nasa.gov/OCO2. Now, there are other team members that may chime in during the Q&A period, but our key participants and speakers will be as follows. First up, Michael Freilich, Director, Earth Science Division, NASA Headquarters. Anne-Marie Eldering, OCO2 Deputy Project Scientist, the Jet Propulsion Laboratory in Pasadena. Junji Liu, Research Scientist and first author, also at the JPL Lab. And Scott Denning, Professor of Atmospheric Science at Colorado State University. And with that, I'll turn it over to Mike Freilich. Mike?
Thanks, Dwayne. NASA's Orbiting Carbon Observatory research satellite, called OCO2, was launched on July 2nd, 2014. OCO2 measures atmospheric carbon dioxide concentrations with the aim of shedding light on the kinds of and balances among the many complex natural processes that exchange carbon between the land, the ocean, and the atmosphere. Somehow, these natural air-sea and air-land exchanges, on average, remove about half of the carbon dioxide put into the air from fossil fuel burning each year. Although for reasons that we don't yet entirely understand, some years almost all of the fossil fuel carbon dioxide is removed from the atmosphere, and some years almost none of it is removed. Can we run the first animation, please? Since soon after its launch, OCO2 has been making frequent, accurate, fine-scale measurements of carbon dioxide over the entire globe, and NASA scientists have been analyzing the OCO2 data to learn about our planet. The OCO2 measurements allow us for the first time to observe quantitatively how our planet breathes with the seasons, with carbon dioxide concentrations increasing in the northern hemisphere during the winter and concentrations decreasing during the summer when photosynthesis on land and in the ocean takes CO2 from the air. But many detailed questions remain, especially regarding the carbon-regulating roles of and balances between natural processes such as floods, droughts, and fires in the tropics and the southern hemisphere. OCO2 is helping us to find the answers to some of these key questions about our home planet. Today, the prestigious journal Science is publishing a collection of groundbreaking research papers made possible by the OCO2 measurements, some of which we will describe for you in the next few minutes. What we'll hear is that the Earth is indeed complex, with many different natural processes regulating air-sea and air-land exchanges of carbon. Analyses of OCO2 data show that some processes dominate in specific geographical areas, seasons, and environmental conditions, while other processes take on greater or lesser roles in other times and places as conditions change. Fortuitously and importantly, the massive 2015-2016 El Nino climate event perturb dynamic, thermodynamic, and precipitation conditions in the atmosphere in the ocean. To put that into English, it is that the El Nino abruptly and significantly changed weather patterns and ocean surface conditions over the entire globe, and especially in the tropics. OCO2 measurements wonderfully detected a variety of changes in the regional and temporal distribution of atmospheric carbon dioxide concentrations. The changes wrought by El Nino and the OCO2 measurements illuminated some of the contributions of specific natural processes and provided hints as to how the balances between processes might evolve in a changing environment. What you will now hear from my colleagues, the people who actually did the work, are important and timely examples of how, by developing cutting-edge satellite technology, using the unique vantage point of space to monitor the Earth, and performing focused, world-leading research analyses, NASA is providing our nation and all of humanity with a better understanding of our complex yet wonderful planet. I'll now turn it over to Anne-Marie Eldering.
Thanks, Mike. In both 2015 and 2016, measurements from OCO2 and NOAA measured the largest annual increases in atmospheric carbon dioxide in at least 2,000 years. The increase each year was 6.3 gigatons or million tons of carbon, or about 3 parts per million of carbon dioxide in the atmosphere. In recent years, the annual average increase has been more like 4 gigatons of carbon, or 2 parts per million of carbon dioxide. These record increases took place even though the emissions from human activities are estimated to have remained roughly the same as in the preceding year, 2014. So what caused this unprecedented increase? Please turn to Figure 2. An obvious suspect was the El Nino of 2015-2016, one of the largest on record. Scientists have long theorized about the links between increases in atmospheric carbon dioxide and El Ninos. Now, thanks to OCO2, which from its vantage point in space is able to make roughly 100,000 measurements per day across the globe, we can answer such questions. Today, we present clear evidence that the heat and drought resulting from the 2015-2016 El Nino were the primary causes of this record increase in global atmospheric carbon dioxide. Specifically, we show that Earth's tropical continents were responsible for more than 80% of this increase. Now, if you'll turn to Figure 3, I'll highlight our key findings, specifically that the OCO2 data show carbon emissions from all land areas increased by 3 gigatons due to the 2015-26 El Nino, compared to a reference year with normal tropical weather, 2011. To put that in perspective, that is equal to almost a third of all the carbon dioxide emitted from human activities during that same time period. 80% of this increase came from the forest in 3 tropical land regions. Our studies quantified the increase in carbon emissions from the tropical forest at 2.5 gigatons. And in addition, we conclude that each tropical land region contributed to the increase and responded to the increased temperatures and decreased rainfall differently, with implications for their ability to continue absorbing carbon in the future. So why is this also important? Because the global atmospheric carbon dioxide concentrations continue to rise, warming our planet and affecting climate. This new finding implies that if future climate brings more or longer periods of drought, as the El Nino did, it may result in more carbon dioxide remaining in the atmosphere, further warming our planet. We know that emissions from human activities are the primary driver for increasing atmospheric carbon dioxide concentrations. We also know that Earth's land and ocean remove about half of the human emissions. However, there's still things to learn about the roles of land and ocean in a changing climate. An event like the 2015-2016 El Nino gave us the opportunity to understand how the Earth's natural systems respond to large changes in temperature and precipitation that come with El Nino. This understanding will give us insights into how our planet will respond to increased global carbon emissions in the future. Before we present the results in detail, let me take a minute to give you some background that might help you better understand them. The concentration of Earth's carbon dioxide is constantly changing in the atmosphere. If you turn to the next figure, figure 4, we see an animation of a portion of the Keeling curve. The carbon dioxide concentrations change from season to season as the plants grow and die, with a high in the northern hemisphere winter and a low in the northern hemisphere summer. But we can also see carbon dioxide slowly and steadily increasing year to year since the illustration here of 2000. The size of the seasonal cycle and the annual increase are determined by a delicate balance between the Earth's atmosphere, ocean, and land. Each year, a different amount of carbon dioxide is taken up and released by the ocean and by the plants and trees. The amount of carbon released into the atmosphere as a result of human activities also changes each year. As mentioned earlier, on average, Earth's land and ocean remove about half of the carbon dioxide released by human emissions, but every year is different. In some years, these natural processes remove as little as 20% of the human emissions, while sometimes they scrub as much as 80%. We knew the El Nino events were one factor in these variations, but until now we did not understand at the scale of continents and regions what processes were most important. OCO2 data are allowing us to study this question on a regional scale. Junji will now summarize her findings about the important roles of the tropics played in recent unprecedented global carbon dioxide increase.
Thanks, Marie. I'd like to present more details about our findings. Using OCO2 data, we quantified how each of the tropical land regions contributed to the observed large growth in atmospheric CO2 during the 2015-2016 El Nino. As our point of comparison, we chose the year 2011. In 2011, temperature and the rainfall were normal over the tropical land, and the tropical terrestrial biosphere was close to carbon neutral, meaning that the amount of carbon absorbed by the biosphere that year was in balance with the amount of carbon it released. As you will see in Figure 5, each of the tropical regions contributed roughly the same amount to the record CO2 growth in 2015. In total, the 3 tropical land regions released 2.5 gigatons more carbon into the atmosphere than they did in 2011. Our analysis shows that changes in the flow of carbon dioxide from tropical land masses were almost equal to the changes in the atmospheric CO2 growth rate in 2015 relative to 2011. This indicates that the increased carbon release from tropical land areas drove the anomalous large increase in atmospheric CO2 in 2015. The OCO2 satellite allowed our team to quantify how the net exchange of carbon between land and atmosphere in each tropical region was affected by the 2015-2016 El Nino. Though the 3 tropical regions contributed roughly the same amount to the growth in global atmospheric CO2, temperature and the rainfall changed in different ways on each region because of the El Nino. Correspondingly, the carbon cycle responded to these changes in very different ways, as shown in Figure 6. In eastern and the southeastern tropical South America, including the Amazon rainforest, severe drought spurred by the El Nino during the second half of 2015 made 2015 the driest year in the last 30 years. Temperature were also higher than normal. These drier and hotter conditions reduced photosynthesis, meaning the trees and the plants absorbed less carbon from the atmosphere. The net effect was to increase the amount of carbon released into the atmosphere from this region. In tropical Africa, rainfall was normal based on our analysis of precipitation, which combined satellite measurements with rain gauge data, but ecosystems endured hotter than normal temperatures. Dead trees and plants decomposed much more, resulting in more carbon released into the atmosphere. Well, tropical Asia had the second driest year in the last 30 years. The increased carbon release here was mainly due to an increase in peat and forest fires, primarily from Indonesia. The fires included an Indonesian peat fire in October 2015 caused by a combination of land clearing, drought, and heat. The fires released peat carbon that had accumulated over thousands of years. To understand the process by which each of the tropical regions responded differently to El Nino, as shown in Figure 6, we combined OCO2 data with data from other satellites, such as carbon monoxide measurements collected from an instrument on NASA's Terra satellite. Carbon monoxide is an excellent tracer for fire carbon emissions, so the instrument's carbon monoxide data helped us quantify the carbon emissions from fires. Figure 6 summarizes two of our primary findings. First, the increased release of carbon from the tropical terrestrial biosphere was responsible for the large increase in atmospheric CO2 growth during the 2015-2016 El Nino. Second, each tropical region had a different reason for its increased carbon release. The 2015 drought and heat patterns over the tropics were similar to what we expect to see in the future and the climate model projections. Understanding how the carbon cycle in these regions responded to this recent El Nino will improve our predictions of how these regions may respond to similar conditions in the future. Now I will hand it over to Professor Denning.
Thanks, Junji. Well, this is really exciting. I've been working on this problem for more than 25 years, and this is the first time we've ever had data like these for the tropical forests. We've known for decades that El Nino influences the productivity of tropical forests and therefore CO2, but we've had very few direct observations of the effects. It's hard to observe these forests, partly just because they're so remote. It's hard to get out there. There aren't very many field stations. And also, thunderstorms in the tropics are constantly mixing the CO2 up into the atmosphere, so surface measurements aren't very good for understanding the uptake and release because the CO2 gets diluted, by the thunderstorms. So if you go to Figure 7, which is another animation here, a subset of climate models, about a third of climate models predict that El Nino-like conditions will increase over the coming decades and suggest that the Amazon in particular will really get hit by heat and drought. In these climate models, the forests take up less CO2 and they release more, so they make climate change a lot worse. And it's important to measure, not just in a greenhouse or a field station, but across whole tropical forests, just how hard the El Nino drought and heat hit those forests and how they'll respond to those changes. OCO2 has given us two different revolutionary new ways to understand the effects of drought and heat on tropical forests. First of all, the instrument directly measures CO2 over these regions thousands of times every day, and also senses the rate of photosynthesis by detecting fluorescent chlorophyll in the trees themselves. We're fortunate that soon after the mission began, this huge El Nino developed, which clobbered rainfall in the tropics and also produced extreme heat in some regions. This was a big natural experiment that allowed us to observe the real Amazon and Africa and Indonesia and use those responses that we saw in the real world in a quantitative way to test our understanding of whether tropical forests will make climate change worse or not. Over the past 20 years, NASA has developed an amazing observing and modeling system that combines many kinds of satellite data to piece together forest productivity, fire, weather, and the atmospheric transport of CO2 by wind and clouds. The authors of these papers that we're highlighting were able to use the observations and models to reconstruct changes in photosynthesis and decomposition and fires in response to this biggest El Nino in 20 years. And more important, they were able to understand and document the mechanisms that control how the climate and ecosystems interact. They not only showed us what the forest did, but why it behaves as it does. These results are going to help us understand how drought and heat affect tropical forests, which are some of the most productive in the world. These forests provide food and fiber for 1 billion people that are affected by El Nino. If climate change produces more drought and heat in the future that suppresses the productivity of the forests, then we have to understand how the tropical forests are going to be responding to this drought and heat so that we can better understand and predict climate change. So to summarize, I'd like to give you sort of repeat the key points, and that's in Figure 8 coming up. As has been previously reported, 2015 and 16 saw the biggest increase in atmospheric CO2 that we've ever measured, at least the last 2,000 years, more than 3 ppm increase in CO2 in a single year. The OCO2 observations revealed the cause, the impact of El Nino, heat, and drought on forests, tropical forests in these 3 regions. The forests lost about 2.5 gigatons more carbon during the El Nino than they did in 2011 each year. Each region responded differently, but all of them added to the increase in the CO2, with carbon losses resulting from different combinations of heat and drought that hit each of these different continents. And if future climate is more like the climate that we saw during this El Nino, the trouble is that the Earth may actually lose some of the carbon removal services that we get from these tropical forests, and then CO2 will increase in the atmosphere even faster. So back to you, Dwayne.
Thank you, sir, and thank you, everyone. So now, for the folks on the call, and again, welcome if you just joined us. We're here talking about the research published today in Science from the OCO2 mission. Now we're going to transition into the question and answer, and I'll toss it to our operator to help facilitate that.
Thank you. We will now begin the question and answer session. If you'd like to ask a question, please press *1, unmute your phone, and record your name clearly. Your name is required to introduce your question. If you need to withdraw your question, press *2. Again, to ask a question, please press *1. It'll take a few moments for the questions to come through. Please stand by. Our first question is from Seth Bornstein. Go ahead. Your line is open.
Thank you for doing this. A quick question, I guess either for Anne-Marie or Junji. In the paper, in the one where Junji is the lead author, and in when you and I talked earlier, the number you used was 2.5 gigatons. And when you add up the 3 continents, 0.9, 0.8, and 0.8, that comes up to 2.5. You're using 3 gigatons. Can you explain where the other half of a gigaton is coming from? Can we say that other half a gigaton is El Nino oriented, or is it just unrelated to the El Nino? So I guess I'm trying to understand. Like I said, in the paper you're using 2.5. Which is the better number to use, 2.5 or 3?
This is Junjie. I will address this question. So the 3 gigaton is the difference of the whole land region. So the other 0.5 is due to extratropics. So the extratropics contribute the other 20% to the large atmospheric CO2 growth in 2015-2016 El Nino. However, in some regions, such as Texas, Mexico, absorbed more carbon from the atmosphere due to increased rainfall, while other regions, such as Australia, absorbed less in 2015. This further reinforces one of the major points of this study, that the global effect of CO2 growth is a net of specific regional carbon exchange processes. So only long-term global observation coverage can help us better understand the changes of carbon dioxide at the regional scales. Let me define the extratropics. So the extratropics is basically the tropical region we used in this paper outside of this region. So it's extratropics. We define that.
So basically everything outside of the tropics, including Arctic, Antarctic, and all that. And we're only talking land for the 3 gigaton change, right? Not ocean. What was the change in ocean we're seeing?
Anne-Marie will address this question.
Thanks, Junji. So, Chef, I think the question you're asking is that sum of 3 gigatons that Junji reports is her analysis of land areas. We did not, with this research, come up with an estimate of the total flux in the global oceans. You know there's a specific piece about the equatorial Pacific, but we don't have an estimate for global ocean exchange.
Okay. Thank you.
Our next question is from Dave Mosher. Go ahead. Your line is open.
Hi. Thank you, guys. Can you hear me okay?
Yes.
Great. So actually, two-part question. The first is, I suppose, for Scott or anyone else who wants to take it, and that is you're talking about the tropics. How much capacity in lay terms are we talking about potentially losing here if heat and drought, sort of suppress the productivity of these tropical forests? I guess how much more would it increase, or at what rate than we're already seeing? And then the second part is more of a political one. So OCO2 was designed to last 2 years. It's now 1 year beyond that, and it's only one of a couple high-precision carbon monitoring satellites studying an incredibly important question of our time. OCO3 has not yet, as far as I understand it, survived congressional appropriations. It's not, the deal isn't inked there. I guess I want to know how critical is that mission as a follow-up or a complement to what's already been done here in the understanding of this problem, and generally what the feeling is. And I suppose the feeling is among the community, the science community that is looking into this research topic. So I suppose this is for Mike and also for Scott, but anyone else is welcome to answer.
So this is Scott. I guess I'll go for the part one there. What we're reporting here is on the impact of this one big heat and dry event in the tropics. But your question is really about how bad could it get if it really if we had these kind of events, this kind of climate in the longer run. I would point you to previous work from climate models that are coupled with the land and the carbon cycle that show upwards of a couple of hundred ppm that you could get in the atmosphere if you wind up actually killing off these forests. But that's certainly not in the cards, tomorrow or anything. This is just a model simulation. The key result here is that we've got actual response of real tropical forests to a real big heat and drought event, so you can test some of those models and evaluate the realism of those simulations.
Okay, thanks, Scott. And this is Mike Freilich. I'll take the second part of the question. So OCO2, as many of our instruments and missions, had a 2-year design life. But frankly, in the rather benign environment of space, once you get through launch and commissioning and infant mortality, the NASA designed and launched instruments tend to last for significantly longer than their design lives, sometimes as long as a decade or even 2 decades. So and there's no evidence at all for OCO2 of any sort of long-term degradation or anything yet in the mission. We look forward to continuing the OCO2 measurements at the same high quality to allow the same incisive analyses that you heard about today for a good long time. With respect to future NASA carbon measurement missions. Actually, in the President's FY18 budget proposal, there is actually full funding for a new mission called GeoCarb to take the next technological step for measuring carbon dioxide from space from geostationary satellites to make even more frequent, higher resolution measurements than are presently being possible from the polar orbiting OCO2 and related international partner spacecraft. So, and GeoCarb is scheduled for launch in the 2022 timeframe. So the outlook for ongoing carbon dioxide measurements from space is actually quite bright.
Operator, can you repeat the directions again, please?
Yes. As a reminder, please press star 1 on your phone and record your name if you have a question. Our next question is from Seth Borenstein. Go ahead. Your line is open.
Thank you again. Because some people with certain agendas might look at this differently, I'm wondering, can you put in context the El Nino effect on CO2 levels in the atmosphere versus historically the anthropogenic effect? In other words, some people might look here and say, hey, look, this is mostly natural, what we're seeing happening in terms of the carbon dioxide in the atmosphere, in the warming, whereas you're talking this is a momentary thing. I'm wondering, can you put this in context compared to the forcing overall by humans historically?
Henry, is that you?
I was going to ask Professor Denning. I'm sure he's addressed this in a lecture.
All right, I'm happy to take this. So for this particular study, as I think was explained in the briefing, that the annual emissions of CO2 was almost constant at about 10 gigatons a year of carbon, and the increase in the atmosphere was about 6 gigatons of carbon. The contribution of the El Nino is to reduce the strength of the uptake of CO2 by land and oceans. So we used the number 2.5 gigatons of carbon was released due to the drought and heat in the tropical continents, and that should be compared to a background, fossil fuel emissions of about 10. So roughly 25% of the total emissions by, global civilization in those years. Now, historically, of course, we've been burning coal, oil, and gas for a long time. So 2.5 gigaton release per year from the tropical continents in a short period, a couple of years of an El Nino, is small compared to the total amount of fossil fuel ever burned by civilization. But in this period, which is, after all, like the highest emissions, the flat emissions the last 3 years, it's about 25% of total fossil fuel emissions. So it's certainly a substantial chunk of the carbon budget for this couple of years.
But it's still not as big as the human footprint.
Correct, by a factor of 4.
Yeah. All right, great. Thank you so much.
No problem.
We show no further questions at this time.
Thank you, Operator. Well, folks, I like this short and sweet. Congratulations, great talent, great graphics, and a great story. Obviously, our folks are here to take additional follow-ups. Please go to the website with the release and the graphics and other material. And I want to thank you all for joining us today, and congratulations. And, Operator, you can close us out.
That concludes today's conference. Thank you for participating. You may disconnect at this time.